only difference here is that this is now the radius of the Earth that we're going to use, not a distance to some satellite. Let's use the simpler version of the period equation. We have 4 pi squared over 9.8 times the radius of the Earth, which was 6378 kilometers, and then multiply that by 10 to the third. So let's try here. 4 times pi squared times 6378 times 10 to the power 3 divided by 9.8, and then square rooted, we get 5,068 seconds, period. 0.85, and then divide that by 3,600 seconds is 1 hour. So divide that by 3,600, 1.48 hours. So if the Earth had spun 1.4 hours, every 1.4 hours, that's really fast. Right now it spins every 24 hours. So if it had spun about 24 or 22 times quicker, very quick, every 1.4 hours, then the people standing on the surface of the Earth would be like a satellite, essentially. So they would be floating, and we would not be able to retain ourselves on the surface. So you can kind of see the application of Kepler's law there to satellite motion and to people standing on the surface. Okay, good. Let's now go back to a problem. I wanted to finish up that last problem that I was doing on gravity, and I wanted to add a couple of comments on that satellite motion problem. So remember, okay, so I wanted to mention about this. When I solved for how many days, I made a slight error. So I wanted to correct that. I wanted to make an errata. Remember, we were solving for, we said E initial plus delta E is equal to the E final. And then the E initial, I put down 0.945, which is the total initial energy, gigajoules. And the loss of energy was negative 0.001 gigajoules times the number of days, and I put that equal to the final energy, right? The mistake that I made is that the final energy, I put down negative GMM over d mu, but that's only the potential energy, right? So that's the mistake that I made. I should have put 2 here. So when I want to know the total energy initial plus how much energy it's losing, it's equal to its total energy that it has. So it's got kinetic energy, and that's positive. On top of that, it has potential energy, which is negative. So you need to have the 2 here. So then, if you using this result, d mu, well, d mu is half of the old d. So you're left with negative 0.945 gigajoules minus 0.001 gigajoule times n equals minus gmm over 2 times half of d, and then half and half, the half and the 2 cancel, and you're left with negative gmm over d, which was negative 1.85. So before, what I did is I didn't have this half, I didn't have this 2 here, so then the 2 went up, and the answer I got here is 2 times 1.85, I got 3.7. So I got a smaller number. Now it's negative 1.85. So now if I solve for the n, it's going to go over to the other side. This is going to come over to this side. I'm going to have 1.85 gigajoule, negative 0.945 gigajoule is going to be 0.001 gigajoule times n, gigajoule, gigajoule, gigajoule cancels, so you're left with 0.945, because this is essentially just double that, okay? Which actually does make sense, because if the distance that it is from the Earth is halved, then the potential energy is, the total energy is twice, okay? But it's more negative. So it's, instead of being negative 0.945, it's negative 1.85, and then that goes to the other side as 1.85 minus 0.945, we're left with 0.945, divided by 0.001 is the number of days, which is 945 days. And then converting that to years, you get 2.59 years, which is a lot quicker than what I got last time. Okay, so because I didn't include the 2 here, so basically what ended up happening is because I didn't include the 2, the equation acted like I was going to lose more energy than I was. So it was going to take more number of days, okay? But actually it takes only 2.59 years. So essentially you have here, this is the Earth. Let's say the geosynchronous orbit was here. Let's say somewhere here is the geosynchronous orbit, and then you go to halfway between that, like that. So you go, you spiral inward, you spiral inward, you spiral inward, you spiral inward. But while you're spiraling, you're losing energy at a rate of 1 megajoules per day, okay? But you have potential energy and you have kinetic energy constantly, right? So you're spiraling, spiraling, and then you'll finally end up halfway. And then if the total energy that you had here was negative 0.945, the total energy that you have here is negative 1.89. It's more negative, okay? Yeah, this one is negative 0.945, this is negative 1.89. Before, what I had done is I had essentially made this double that. I had made this 3.8, something like that, double that, negative 3.8. So essentially, it had acted as if it had to go all the way down to here, you know, like that, until it's here. So essentially, I had done it 4 times this, okay? So 4 times 0.945 would be what? 0, 2, 16, 18, 1, 36, 37. 3.78, right? 16, 18, 1, 36, 37, yeah, 3.78 joules. Okay? So the answer that I got last time, which was 2,000 something days, right, 7 years, that's the amount of time it's going to take to get to quarter of the original distance. So if the original distance was d, this distance is half d, this distance is quarter d, okay? So this thing is going to take, let me calculate here, just to remind us here. 2 times 1.89 minus 0.945. Divide that by 0.001. Divide that by 365.21. It was 7.76 years. So basically, from here to here takes from here to here takes 7.76 years. Okay, and then this one here, from here to here, takes 2.59 years. 0.945 divided by 1,000. Uh, 2.59 years, right?